Hello, everyone. Welcome to this webinar on automated mesh refinement and advanced physics for rotating machinery with SimScale. I'm your host and presenter, Kanchan Garg, product manager for rotating machinery. And joining me today is my colleague, Ajit, who is a senior application engineer and one of the experts in our product, who will also be showing you a demo of the new features that we have for rotating machinery. Let's take a quick look at the agenda for today. I will start with detailing a little bit about our offering for rotating machinery simulations, focusing on some of the latest features that we have released as well as what's coming. This will be followed by a demo of a vertical axial pump by Ajit, and of course, the question and answers at the end. Before we proceed any further, just a quick note that all your mics will remain on mute. But we have our moderator, Monique, handling the chat. So should you have any questions, please feel free to use the chat and she will help you out. So for about a decade now, SimScale has been breaking down the traditional barriers to simulation by bringing cost-efficient and easy-to-use simulation to the cloud, which basically means that we are driving the hardware and software footprint of simulation to zero. And about a year ago, we extended this vision to the rotating machinery industry, where we endeavor to bring accurate simulation to the cloud, making it really fast, and because of the platform, accessible to different teams across companies and across the product life cycle, and also covering a broad range of applications within this industry. Let's take a look at how we do this. So from the beginning, SimScale has been an end-to-end simulation tool with embedded geometry and meshing and different types of physics that you can solve, including solid mechanics, heat transfer, and fluid dynamics, and an inbuilt post-processor. And underneath this all, we have the infrastructure that takes care of all the data management requirements, IT, and licensing arrangements, also offering usage-based licensing. And this is packaged within a web interface that can be accessed simply through a web browser, making it truly accessible from anywhere, at any time, and at any scale. And we add a layer of further enhancement to it by way of our APIs, which make it possible to integrate SimScale into the workflow, other digital workflows within your organization, and bring your company one step closer to full organizational digitalization. Now let's take a look at the actual physics, the theory behind our offering for rotating machinery simulations. As I mentioned before, it is an end-to-end multidisciplinary analysis where you can carry out structural, CFD, as well as thermal analysis within SimScale. And our most recent investment has been in a proprietary CFD solver that is specifically designed for rotating machinery applications. It is fast because it's cloud native, and you can get steady state runs with as less in 30 minutes. And we have consistently achieved 2 to 3% of accuracy margin of experiments. Some of the capabilities that we have released include transient analysis and automated performance curves. This is something that we had covered in our previous webinar. And we have also recently released cavitation, which I will touch upon a little bit in the following slides. Staying true to our commitment to versatile solutions, we are developing this tool to be able to address different types of physics, a wide range of applications across the rotating machinery industry. And here are some of the examples that you can see of the simulations that are possible within SimScale. Now, a little bit news about the overall SimScale product, which has been developing pretty fast too. We now have on-shape CAD associativity, which makes it easy to rerun your designs with multiple versions of the CAD or assembly simply through the click of a button. And adding on to our parametric studies features where you have several sub-runs and sub-iterations of a particular design, we have introduced the ability to have visual result comparison, where you can bring up any two designs, put them side by side, and compare them, see how they match each other in terms of velocities and pressures. It is also now possible to have your very own custom material library where you can create your materials that you can use across projects. And we are further adding to this by enabling material library for the whole organization that can be shared between different users in a company. And more such features upcoming include automation of the rotating regions creation within SimScale and further streamlining of how you define a rotating zone, be able to have qualitative numerical comparisons between two plots or two quantities in a 2D data. And of course, a very important thing that we're working on is SolidWorks CAD associativity. Specifically with respect to rotating machinery, we have now implemented mesh refinement in our proprietary solver Subsonic, and that is what Ajit will be covering in the demo later. What we have observed is that with mesh refinement, meshing becomes even more robust, faster, and reduces simulation times. Here is an example to solidify what I just said. And we have also released cavitation. I am not going to go into a lot of detail about cavitation right now. We have another webinar coming up, and I would like you to register for that to know more how you can use cavitation and include its effects early in the design process. And a quick peek on what's more to come in terms of the product roadmap. Exciting things that we have already included, and our pace of development is very fast. We are now working on implementing real gas models, rotodynamics, as well as multi-phase within our proprietary subsonic solver. And we are focusing heavily on extending the parametric studies features by extending it over different inputs, manipulation of your output, so that you can actually customize your performance curves depending on the use case that you have. And through it all, our focus has always been on how to make your workflow, your experience smoother and faster. And these are some of the features that I talked about before, like automation of the rotating region, streamlining of how you give the rotating inputs. Those are some of the features that fall under this category. And now, without further ado, the most exciting part is to take a look at the product itself. And for that, I hand over to my colleague, Ajit.
Thanks, Kanchan, for the brief overview of what SimScale is working on recently and what are the new features that are going to be released in the near future. In the next few minutes, we'll be taking a look at the live demonstration of an vertical axial pump and focus on three main points here. The first one about the newly released zone refinement for subsonic analysis, and we'll also take a look at some of the insights that we can get from the post processor. And finally, we are also going to see how we can easily switch between a steady state and a transient simulation for the subsonic analysis. For this purpose, we are going to take a vertical axial pump, and the pump consists of a suction bell mouth combined with an impeller and a stator or guiding vanes setup. And we're also considering the effects of pump shaft and an elbow for the discharge. For users who are new to SimScale, SimScale is a completely cloud-native simulation tool. All you need to access high-fidelity simulation is to have a simple browser and an internet connection. You can log on to simscale.com, enter your credentials where you can access the dashboard. The dashboard is where you have all your projects listed, where you can create a new project or even jump onto an existing project and start simulating. For this particular webinar, we'll focus on the axial pump analysis, where we have two different designs of the pump, and we would like to see and compare the flow characteristics within this pump. To start with, we'll go with the design 1 and create the simulation. This is where you select the physics for your analysis, and for all the rotating machinery and flow control devices like valves, SimScale has invested quite a lot on the subsonic module. We'll go ahead and select the subsonic module and create the simulation. From this point on, it is a simple top-down approach where you can set the materials, boundary conditions, and start your simulations. You might also notice that the imported CAD model has a lot of topological entity sets. And these are useful for CAD associativity, where In your CAD tool, you can name your faces according to the boundary conditions and the regions for assignment and bring it in within SimScale as they are preserved as at the input. So here for this CAD model, we have a set of faces which represent the impeller. We have a set of faces which represent the housing walls, outlet, rotating zone, and flow region. So for the material properties, we can go ahead and select water and select the flow region. We do the same for boundary conditions. Here in this case, we have a pressure inlet where the inlet face is assigned with 0 Gauss pressure or total pressure. And for the outlet, we have a velocity outlet at a particular flow rate. And once again, we go ahead and select the outlet face, which is generated from the CAD. For the rotating region, you can create a rotating region, set your rotational velocity, for example 209.4, which corresponds to the 2000 RPM, and set the axis of rotation. The axis of rotation actually follows the right hand thumb rule, so you set the axis and also the direction and select the rotating region for your assignment. Once again, if you're analyzing a pump, you're mostly interested in the efficiency of the pump, and to calculate the efficiency, we need the shaft power and the fluid power. To capture all the power values, you need to assign a result control item which captures the forces and moments, and here we select the faces of the impellers. To capture the pressure difference, you can go ahead with setting a pressure difference where the inlet and the outlet faces are assigned here. All the settings are done, and next, before starting the simulation, you can set the fineness of the mesh here. There are two ways that you can set the fineness of the mesh. So one, you can give an automatic fineness level ranging from 1 to 10, with 10 being the finest. And with SimScale recently released the region refinement, where in case of validation, where you are trying to focus on the last few percentages of efficiency when compared to the measurement data, you can also go ahead and set a refinement region. For the refinement region, you'll be able to actually set the refinement within a particular region in your geometry by focusing that using a Cartesian box or a cylinder. For this case, we'll go ahead and create a cylinder with a particular radius and set the axis of the cylinder and also the reference point here. Once when you're happy with your region refinement, you can go ahead and set that as your region refinement and set the target size of cell within this particular zone. We'll go ahead with 5 centimeter and start the simulation. And now we have the design 1, which is actually selected for the simulation, and to switch from the design 1 to 2, you don't need to start everything from scratch. Since you have a confident setup that you have, you can go ahead and duplicate the entire setup so that you get a copy of it and then select the geometry that you would like to simulate. For example, instead of design 1, you will swap it to design 2 and save this simulation. As you can already see, most of the boundary conditions are preserved and all the face selections are also preserved. This is because of the CAD associativity. And right now, all you need to do is start the simulation for design 2. Thereby, we have started the simulation on design 1 and design 2, and after the results are generated, you can start comparing the results. Before getting into the post-processing, we'll also take a quick look at how we can quickly switch between a steady state and a transient run. For example, if you have the design 1 which is running here, you can again duplicate the entire setup, and on the top level of your simulation tree, you have the option to simply switch between the steady state and transient analysis. Once when this switch is done, all you need to do is start the simulation again. This will take care of the background simulation settings with respect to the transient analysis. Next, we'll quickly focus on how the results compare. So let's take a look at the design 1 and see how the flow behaves within this pump. Once when the results are loaded, we'll be able to plot design with different filters to take a look at the results. There are several filters that you can access from, such as cutting plane, particle traces, iso volumes, and a few interesting ways can be making a section view of your geometry and seeing how the flow looks like at a particular region. So right now we have a cutting plane at the midsection of your geometry, and this is plotted with the velocity. You can already see that the blue regions are low velocity regions, and the red to or yellow regions are high velocity. You can also range the velocity according to the gradient, but for this case, if you take a deeper look at the results, you can already see that the flow is imparted with a high rotating velocity when it leaves the stator. And that's why the vectors are plotted on outwards one direction, and on the other side it's plotted on the inward direction. You can also take a look at the flow in real time by plotting the particle traces. So let me quickly change the transparency of the geometry and plot the particle trace to see how the flow looks like. An initial look already gives you a good amount of insights about how the flow behaves near the impeller and how it travels across the stator blades and is imparted with the rotational velocity. Right now we have the second design which we would like to compare with a set of guiding vanes on the rotor shaft to make sure we are decreasing this rotational velocity, which will again directly affect the efficiency of the pump. To compare the results between two runs, you can simply click on compare and select the run which you would like to compare. For now, we'll go ahead with the design 2 and let the results load for comparison. Once when the results are loading, you can have a synced view on both the results, where either you change the filter or or manipulate the model. This will be reflected on the other design as well. Right now you can already see that when you're manipulating design 1, the views are synced so that you get a good view about the comparison here. And here again, plotting the cutting plane will show you how the results look like on the internal section of your geometry. Here you can see that the vectors are starting to move upwards when compared to the first design, just because of the guiding vanes which are present inside. Remember, we have also started the meshes with refinement, and to check the refinement, we'll quickly get back to this slide and see how different the mesh looks with and without the refinements. Here on the left, you see the automatic mesh just with all automatic settings, and on the right, you see the automatic settings along with the region refinement. And you can already see, for a simple simulation study, you can use the automatic mesh, which captures pretty good on the surfaces as well as the flow region. And if you're looking for a validation stage study, then you can go ahead and create a rotating or refinement zone to make sure the flow features are captured properly. Perfect. Now what we are able to see today is run different simulations with different designs with minimal effort, thanks to the CAD associativity. And apart from that, we also took a look at how the region refinement can help you focus the mesh on the important regions and optimize the runs. We were able to also see how we can go ahead and run different runs in parallel and compare the results side by side. This is all for today, and I'll be opening up this stage for questions. Thank you.
All right. Thank you. Thank you so much, Ajit and Kanchan, for that insightful and really thorough presentation. I do see that we have some questions here. So let us move over to these questions. First one, is a result comparison available across all solvers of SimScale?
Yes, so yes, it is available across all analysis types. It is actually a feature within our inbuilt post-processor. So as long as you have simulations and designs within your project that you want to compare, you should be able to use it.
Okay, great. Thank you. Here we have another one. What turbulence model does the subsonic solver use?
Maybe I can take the question, Kanchan.
Sure. Yeah,
Yeah,
please.
sure. So the subsonic module predominantly uses the K epsilon turbulence model, and it's well validated against a lot of measurement data where, as my colleague Kanchan mentioned, we are able to hit about like 2 to 3% of experimental result accuracy.
Thank you so much. And this one kind of follows onto that. Can you animate a trace, a particle trace?
Sure, that's also an interesting question. So as you saw on the live demo, we were able to plot the particle trace with cylinders, but you can also animate them by simply using a comment visualization. So you can cut down the particle traces into bits and then animate that to see how the flow moves around the housing or any other region that you are interested in.
All right, all right. Just kind of scrolling through here, just trying to get through as many questions as time permits. What different refinement zones can be given for each, for mesh refinement?
Okay, I can take that question. That's the So with respect to subsonic, right now you can create geometry primitives that are cylindrical or box in shape. And it could be around your impeller or rotor or behind the rotor if you wanted to resolve the wake. But at the moment, we support box and cylindrical geometry shapes.
All right, thank you for that. And what is the best practice to determine the target cell size within a refinement zone?
Probably I can take the question, Kanchan. Yeah. So as you have already seen, for most of the rotating machinery components, you'll be mainly focusing near the impellers, or if you have stator or guiding vanes, then you can actually refine them. The best practice here from our side will be if you have a narrow channel, make sure there are at least 3 cells across the thickness of the channel. And if you're refining the rotating zone, make sure between each blade, the gap should be refined starting with like 10 cells. And then if you want to achieve higher accuracy, you can actually go more or go less according to your requirements.
It's very interesting. Thanks, Ajit. I think we have time for a couple more. Here's an interesting one. Can you make the rotational speed a parameter that can be swept or solved at multiple points?
Perhaps I can take that, Ajit. Yeah.
Yeah, sure, Kanchan. Yeah.
So at the moment, you can change the rotational speed, and as Ajit showed that it is pretty easy to do that. Like while your simulation is running, you can go back, change an input, and launch another one. We are working on parameterizing this as well, so that just like flow rates, you should be able to even upload like a table of RPM, and just with one click of the button, run your entire sweep for the performance curve.
Got it. Okay. All right. Well, thank you. Thank you so much. Thank you so much, Kanchan and Ajit for taking or questions. I would like to just give us an opportunity to reach out to SimScale via our website. You can go to our website and access the request for a demo there as one way to reach out to us, or you can email us directly, and we will be sure to get back to you within one business day. Thank you all for joining us, and we appreciate your time and participation. We hope to see you again at another event. Thank you.
Thank you.
Thanks all.